welcome to Best Tutorials, and in this video I'll be doing practice problem 14.5. So just continuing where I left off a few months ago. So let's see. So here's the question, practice problem 14.5, and it says construct the board plots for, so this is the transfer function that we're given, and we're supposed to construct the board plots which correspond to this transfer function. So let's have a look at what we have. And now S being equals to j omega, making this conversion, we can convert this into h omega. And after doing that, we'll basically want to match the poles or roots with the standard forms that we know about. So the simple pole, the pole at the origin, zeros at the origin, but as you can see here, we don't really have zeros, only have poles because the roots are below or at the denominator, right? So now after making this conversion, the next step would be to have the poles in standard form. So let's go ahead and do that. But first, I think it's best to work with the S variable first before we make the conversion, because then we can just simplify whatever we have here and then just substitute this conversion over there. So doing that, let me just go ahead and do that. At the bottom, we just have S. And if you were to try and simplify this equation over here at the bottom, which is a quadratic equation, there are quite a few ways that you can do this, right? And one way that you can actually do this is to factor out the 400. Now if you factor out the 400, you have s squared divided by 400. You have 80 divided by 400 s, and then finally 400 divided by 400, which is basically 1. I shouldn't actually be doing this because we just took out the 400, and that is the reasoning behind it, and closing this other bracket because we're now dealing with this part only inside these brackets. So now that we have this, we can basically simplify and just cancel that, and you're going to have 1, 5, and in the end this will be the result. So let's clear that up. So what we're doing now is to transform the equation into a form where we can simply extract the poles. So looking at this, just gonna have that over here. So this is as far as we've come. And what you can do now from this point is you can now make that substitution, or you can now make that conversion. But before you do that, we can also include the 400 here in the exponent 2, or it can also have a power of 2 by taking it like this. So you can also take the 400 outside. That is perfectly fine. Now only deal with this bracket. So you can have this. Let's find the square root of 400, and it will have everything inside the square. And this is where we are. Now if you look at this, we can't transform it into any of the standard forms that we want to properly identify the poles. So what we can do is to make an approximation, and that approximation we're going to make after basically transforming this. So let's transform this using this transformation, which I previously talked about. So we have this, then we have j omega, then we have 400, then we have j omega divided by 20, then we have that plus 1. So now what we want to do is to extract the poles from this equation, from this transfer function. So doing that, you can just simplify. First of all, you can just simplify this over here, and this is not 1 over 4 but 1 over 40. So there's a shift in the zeros. And now here at the bottom we have this. And if you check this, there isn't a direct way to map it to a standard form. So what we do is we basically take this part and assume or approximate the whole thing. We approximate the whole thing using this approximation. So we assume that it's a repeated pole of this form. So this whole thing is approximated using this repeated pole. So now, as a summary of what we have, so we have a constant at the top, we have a pole at the origin, and we have a repeated pole, right? So looking at the table in the textbook to see the behavior of each of these, we now can draw each of our board plots. So if you just recall the behavior of a pole at the origin, where the n is the exponent, and in this case it's just 1. So the behavior of this would just be, in the magnitude plot, it would be a negative 20n decibels per decade slope, and it would pass through 1, basically pass through 1. That's what we expect in terms of the magnitude. But in terms of the phase plot, we expect a negative 90 n degrees, and once again the n is 1 in this case. So this is the effect that we expect for this pole at the origin. So we dealt with that. Now let's talk about this constant at the top. It's just a simple thing. You just transform it using this, and this is base 10, by the way. And in this case, this k will basically just be the value that we have. And you can just simply go to whatever value it is. We're going to look at that in a bit. And now in terms of the phase, it basically is 0 degrees. So it will be at the 0 degree line. So we have three factors. We have the constant at the top, we have the pole at the origin, and we have this approximation here. So this is the only thing that we haven't talked about. So now this thing here would be of this form, but now it's a pole. So we're talking about this, and once again the n is 2, so it's 2 in this case, and so it follows that we come to the point P, exactly at P, which is the value at the denominator, which is 20 in our case, and now this would be negative 20n, and since the n now is 2, so it would have a slope of negative 40 decibels per decade. And this is a magnitude plot. Looking at the phase plot, we now look at the effect of this. It would be, so if you go to a decade before the p, which would be 2 in our case, so 20 divided by 10, you go to the point 2, and then you'd have a slope which corresponds with your n. So the stopping point is this is the stopping point. Now if your pole is somewhere there, your pole value or your pole point is somewhere there, and your stopping point is 180, and it's a decade later, now you can simply tell that this slope over here is negative 90 degrees per decade, because we're going to start at some point 0 over there, and we're stopping, we have a decade there and another decade there. So 2 decades later, we have this negative 180. So which means for each decade, we actually move by negative 90 degrees. So negative 90 degrees to that point, and then negative 90 degrees again to finally reach the point negative 180. So that is the reasoning behind everything that we're going to do right now. So we can just go ahead and now finally draw the final product using each of the factors and the contribution. So I was just talking about the contribution of each of the factors and how they're actually going to influence the final plots. So now that we have that, we can now come to the side. I guess we can use the side. Let's use the side, and now writing it in terms of the approximation. we want to have this equation so that we don't forget the factors that make up the total plot. So now that we have this, let's start with the magnitude plot. So the magnitude plot, we'd have, or we'd call it H, we'd label this as H, dB decibels, and we draw the line, and let's see what we have. So if you say, or if you take the top factor, which would be, in terms of decibels, would be 20 log of 0.025, then you'd find that it has a value of, so let's have 20 somewhere there, it has a value of about negative 32.04. So we're just going to draw dotted lines to indicate each of the factors for now, right? So that is the constant at the top. We dealt with that. So it might be helpful to actually check all the factors or everything that contributes to your final plot and actually have your final plot with all the factors. So I just put a tick there just to say that we actually have the contribution of that constant over there. And at the bottom, we have this pole at the origin. And now, as we previously said, this would correspond with a negative 20 decibel per decade slope, and it would pass through 1. So let's say 20 is somewhere there. And now at about 0.1, because we want between this point and that point, which is a decade, we want to have a decrease of value by 20. So at 0.1, we expect to have around about 20. And by the time it gets to 1, it would have lost that 20, so negative 20, right? So that is the kind of slope that we expect. And as you can see, I'm not using graph paper or log scale, and this is not exactly accurate, but this is how you do it on a proper log scale. So you'd look for about 0.1 or a decade before 1, and you'd map that to 20. And after that decade, you basically would have lost that because this is a slope of negative 20 decibels per decade. And it might be useful to write these slopes so that when you finally add everything up, you have a proper understanding of what is going on, or you can then add it properly and not struggle or try to remember what the slope was. So it might be helpful to write the slope as well. So now we have that dealt with. We are now dealing with this one. This is a repeated pole. And to deal with that basically has negative 20 n decibels per decade slope. So the n is 2, and we now expect our repeated pole. So we're going to go to the point where we have 20, and this will have a slope of negative 40 decibels per decade. So now if we go about a decade later, which is about 200, then we expect to have dropped by negative 40. So this is what this means, right? So a decade later, we expect to have dropped by negative 40. So this is how you'd map it out, or this is how you'd follow through. And you can also write the slope over there. So now we have all the factors, and all that's left is to draw the final product or the final thing. So doing so, you start on the left on the axis and then see all the factors that you have. And the first thing that you notice is that you encounter this line over here. But instead of starting it where you found it, you recall that we have this shift, which is introduced by the constant at the top. So let's say we had some value over there, and we are now going to shift that value down by this value, which is negative 32. So just above there, then it should fall. So let's say it's 20 something. We aren't sure what the exact value is. You can find that exact value if you want, but it's basically negative 20 something. And if you drop that by negative 32, expect it to fall here just before 20, right? That's where you expect it to fall. It has a value 15 or negative 10 or something like that. So that is the range that you expect it to fall in. So now we're going to start drawing, and now take note of the slope. So this slope will be negative 20 decibels per decade, right? So we're still going and going and going like that. But once we reach this point here, once we reach this point, this is introduced and its effect must be seen. So now from that point, we basically have an introduction of, so this is negative 20 decibels per decade. And at this point, we have an introduction of this additional negative 40. So the slope here would be steep because it's now negative 60 decibels per decade. So that is the point. That is the point behind this. That is the point behind having the factors. You basically want to add the effect of all these factors at a later stage. So you just have to follow along, starting from the left and then seeing the effect of each of the factors, shifting everything accordingly, and then adding the slopes up. So we started off with a slope of negative 20 decibels per decade. Moving along. Now, when this repeated pole starts, its effect must be added to what is already happening. And that is why we have negative 20 and then adding this negative 60. So that would be your magnitude plot. It would basically continue indefinitely like that, because these slopes also continue indefinitely, right? So now that is the magnitude plot, and we can now come to the effect or what will result from the phase plot. So the phase plot, you can call it phi if you want, with unit degrees, because we're dealing with angles here. And once again, we're just going to extract the effect of each of the components. And as we discussed, the effect of the constant will be 0 degrees. So at 0 degrees, that is what we have. So it's basically doesn't do much. It's just at 0 degrees. And now we have a pole at the origin. We have a pole at the origin, which is that there. And that pole would have an effect of negative 90 N. And the N in this case is 1. So it would have a negative 90 degree effect. And that is why I drew that line over there. So we've dealt with 2. We have 1 to go. And that final one, we basically go, as I previously said, go to a decade before, because it is of this form. So we go to a decade before, which would be 2. Then we have the point itself. Then we have a decade later. And how we track all of this is you basically start here. And by the time it gets to this point, it should have traveled by about 90, because the slope should be negative 90 N. So 90 degrees N per decade. And now the N is basically 2. So now that the N is 2, then it's actually negative 45. But the final result, or the final point, is negative 90 N. So please take note of that. So the slope is actually this, right? And starting a decade before, and now having an N of 2, then this would be the slope. Yeah, this would be the slope. And which means that at the point of our pole, we basically have negative 90, and a decade later would have negative 180. So this is how you track all of this, or this is what is actually happening. And once again, you're just going to add the effect of everything. And starting from your left, you'll notice that you only have the effect of this pole at the origin until you reach this point at 2. Once you reach that point, you start having that slope over there. And you continue having that slope. And when you reach this point, which is about 200, when you have this flat line, then this will also flatten out. So you're just adding up the effect of each of the components. So the constant gave a contribution of 0. The pole at the origin gave this, and that is why our graph is actually shifted down to negative 90 to start at negative 90. Then we have a slope which corresponds to this, right? Which is negative 90 degrees per decade. And finally, it flattens out at the stage which is negative 90 degrees N, and which would be negative because N is equals to 2. so it'll flatten out eventually. So this would be your phase plot, and the one which you drew previously would be your magnitude plot. And that is basically how you solve these kind of problems. Basically add the effects of each of the components that make the stuff up, and you're basically done. And if you like this video, just go ahead and give it a thumbs up. If you haven't subscribed, please subscribe. I'll see you in the next video.